September 5th, 1941. Union Pacific's Omaha shops. Through arc-welder sparks and industrial haze, Chief Engineer Otto Jabelmann watched the final bolts torque on Locomotive 4000, a 132-foot monster that would become the longest locomotive ever built for American rails. The maintenance foreman's report sat unopened on Jabelmann's desk. Inside were preliminary calculations that should have stopped the entire project. Bridge load ratings exceeded by margins that made veteran civil engineers question their careers. Rail fatigue projections that suggested catastrophic infrastructure failure within 5 years of operation. Turntable modifications costing millions of dollars that nobody had budgeted for. But September 1941 left no room for engineering caution. Japanese expansion threatened Pacific supply lines. German U-boats decimated Atlantic convoys. America's industrial mobilization demanded freight capacity that existing locomotives could not deliver, regardless of what infrastructure limitations suggested. The big boy represented Union Pacific's answer to an impossible equation: move wartime freight volumes across the Wasatch Mountains using locomotives that wouldn't require constant double heading and helper service. The specifications called for 135,375 pounds of tractive effort, pulling force that exceeded anything American railroading had ever attempted. Standing beside the completed locomotive, Jabelmann recognized something the project's advocates had deliberately ignored during the design approval process. This machine didn't just exceed previous engineering standards, it shattered every assumption about what railroad infrastructure could safely accommodate. The 1.14 million pound weight wasn't distributed across enough axles to prevent concentrated loading that would destroy track structure. The 68-inch drivers delivered torque that could twist rails out of gauge during hard acceleration. The rigid wheelbase created lateral forces through curves that would pulverize ballast and destabilize roadbeds. Assistant Track Superintendent James Morrison had submitted resignation papers after reviewing the preliminary route analysis. His memo to Union Pacific's Board of Directors outlined infrastructure modifications totaling $47 million, double the cost of the locomotive order itself. Every bridge between Ogden and Green River required structural reinforcement. Curves throughout Echo Canyon needed complete reconstruction with heavier rail sections. The company's response came in a single telegram: war emergency supersedes normal engineering protocols. Proceed with operations. Watching the assembly crew prepare Big Boy 4000 for its first steam test, Jabelmann understood they had created something unprecedented in railroad history. Not because the locomotive represented advanced engineering achievement, but because it represented catastrophic over-engineering that prioritized raw power without considering whether the railroad's physical plant could survive that power. The wartime emergency that justified building these behemoths would eventually end. The infrastructure damage they inflicted would remain for decades, creating maintenance obligations that would question whether Union Pacific had actually solved their freight capacity problem or simply exchanged one operational nightmare for another. As steam pressure reached 300 psi and the massive locomotive stirred to life, Jabelmann recognized the terrible irony. They had demanded unstoppable pulling force. They got exactly what they asked for, and within 3 years, every civil engineer on the Union Pacific system would wish they had never approved the project. The Wasatch Grade between Ogden, Utah, and Green River, Wyoming represented American railroading's most punishing operational territory. 80 miles of sustained climbing through grades reached 1.14%, with curves tightening to 20-degree radius, where train resistance multiplied beyond conventional. Locomotive capabilities. Union Pacific's existing 2880 mallet compounds could barely move 3,200-ton freight over this territory without helper locomotives stationed at strategic intervals. The economics looked catastrophic when freight departments calculated actual operating costs. Each eastbound train required 2 road engines plus 3 helpers, consuming 5 complete locomotive crews and generating fuel bills that made competitive freight rates impossible. The 1940 military mobilization transformed marginal economics into an operational crisis. War Department contracts demanded 8,000-ton munitions trains moving from West Coast arsenals to Great Lakes manufacturing centers. Steel mill output from Geneva, Utah required daily consists exceeding anything peacetime railroading had contemplated. Petroleum shipments from California refineries to Midwest distribution terminals created traffic volumes that existing motive power could not handle. Edward Bailey, Union Pacific's superintendent of motive power, faced mathematics that offered only one solution: double existing locomotive tractive effort, eliminating the helper service that consumed resources the railroad could not spare during wartime emergency. The specification document Bailey presented to American Locomotive Company demanded capabilities that seemed theoretically possible through straightforward scaling of proven articulated designs. 4 sets of driving wheels instead of 2. Boiler pressure increased to 300 psi. Firebox grate area expanded to 150.3 square feet, large enough to generate steam production that could sustain maximum tractive effort up continuous grades. ALCO's engineering department calculated that such specifications would create starting tractive effort of 135,375 pounds, exceeding the 2880 mallets by 47%. The performance projections showed single locomotives moving 5 to the 800-ton trains unassisted over Wasatch grades that currently required multiple units. But the analysis focused exclusively on locomotive performance, treating the railroad's physical infrastructure as unchangeable constraints rather than systems that would face unprecedented stress under operational conditions these machines would create. Union Pacific's Civil Engineering Department received the Big Boy specifications in November 1940 with instructions to assess route compatibility. The preliminary survey required just 72 hours to reach devastating conclusions. Bridge number 302 across Echo Creek could not support the 548,000-pound locomotive weight on its existing stone arch construction. The steel truss span at Devil's Gate required complete replacement with heavier members. Wooden trestles throughout Weber Canyon needed conversion to concrete and steel at costs exceeding $2.8 million per structure. Track department calculations revealed that 68-inch drivers delivering 135 375 pounds of tractive effort would generate rail stress exceeding 90,000 psi during hard pulling, forces that would create plastic deformation in standard 131-pound rail sections, permanently spreading gauge and creating derailment hazards. The civil engineering report recommended rejection of the entire Big Boy program, suggesting, instead, that Union Pacific purchase additional conventional mallets and accept the higher operating costs until post-war conditions allowed proper infrastructure upgrades. The recommendation reached Union Pacific's Executive Committee on December 8, 1941, the day after Pearl Harbor, when every consideration except maximum freight capacity became strategically irrelevant to American railroad operations. American Locomotive Company's Schenectady Works, transformed through early 1941 as fabricators, assembled components that challenged every manufacturing capability the facility possessed. The Big Boy project demanded precision engineering at scales that made conventional locomotive construction look like simple mechanical assembly. The main frame casting alone weighed 4,700 pounds, requiring foundry techniques that pushed metallurgical limits. The one-piece bed structure had to maintain dimensional stability across temperature ranges from 40 degrees Wyoming winters to 150 degrees. Firebox radiant. Heat. Any warping would bind the articulation joint that connected the locomotive's front and rear engine groups. That articulation mechanism represented ALCO's most controversial design decision. Chief designer A.H. Fetters specified a massive hinge assembly allowing 19 degrees of angular displacement between engine groups. The engineering seemed sound on paper, permitting curve negotiation while maintaining even weight distribution across all 16 drivers. But Fetters had never calculated the dynamic forces this articulation would experience under maximum tractive effort conditions. When 375 pounds of pulling force transmitted through a flexing joint while negotiating 20-degree curves, the lateral stresses would exceed anything American articulated locomotives had previously encountered. The boiler construction incorporated features that violated conventional wisdom about steam locomotive design sustainability. The firebox used Nicholson thermic siphons, vertical water, circulation elements that increased heating surface area by 18%, enabling the massive steam production rates the specification demanded. But those siphons created maintenance access nightmares. Replacing a failed siphon required dropping the entire firebox, a procedure that would take Omaha shop forces 3 weeks per locomotive. The design prioritized performance over maintainability in ways that would haunt Union Pacific's mechanical department for the locomotive's entire service life. The running gear demonstrated similar optimization for power at the expense of practical operation. The 68-inch driver diameter delivered optimal tractive effort, but created ground clearance so limited that any track irregularity risked catastrophic mechanical interference. Maintenance crews would discover that even minor ballast buildup could cause driving wheel counterweights to contact rail flanges. Most critically, fetters specified main rod bearings using bronze alloy compositions that could theoretically handle the enormous forces the drivers would transmit. The testing protocol verified bearing capacity under static loading conditions but never simulated the shock loading that would occur when 1.14 million pounds of locomotive hit track irregularities at 20 miles per hour. The prototype underwent acceptance testing at Alco's plant using dynamometer procedures that measured pulling force under controlled conditions. The locomotive exceeded specifications, delivering 135 as 960 pounds of tractive effort during the initial test runs. Everyone celebrated the performance validation. Nobody tested what happened when that force transmitted through railroad infrastructure built for locomotives, generating 85,000-pound tractive effort maximums. The gap between laboratory testing and operational reality would become evident within the first month of revenue service. Union Pacific's purchasing department had committed to 25 units before the prototype left Schenectady. The contracts were signed, the manufacturing was underway, and the company had invested resources that made project cancellation economically impossible, regardless of what operational experience revealed. The engineering hubris wasn't building locomotives that were too powerful. It was assuming that everything else in the railroad system could adapt to that power without catastrophic consequences. If you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old trains like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel, and let's keep these old trains' legacies alive. May 1942 brought the first operational reality that locomotive specifications alone could not predict. Big Boy 4004 departed Ogden eastbound with a 4,700-ton freight consist, the moment Union Pacific would discover exactly what 135,375 pounds of tractive effort meant for railroad. Infrastructure built to different engineering assumptions. Bridge 217, spanning the Weber River, had served reliably since 1903, supporting every locomotive Union Pacific operated across the Wasatch Territory. The stone arch structure carried a capacity rating of 620,000 pounds, based on distributed loading assumptions that articulated steam power had always satisfied. The Big Boy crossed at 18 miles per hour under full tractive effort, transmitting dynamic forces that exceeded static weight calculations by margins the original engineers never contemplated. Track department crews heard the sound first, grinding compression as mortar joints yielded under concentrated axle loads that approached 72,000 pounds instantaneously. By the third Big Boy crossing, inspection revealed cracks radiating from the Keystone Arch. Emergency bridge restrictions limited the locomotives to 8 mph crossings with consists under 3,500 tons, eliminating exactly the operational advantages that justified building them. The retrofit required $340,000 in structural reinforcement that consumed materials the War Production Board had allocated for destroyer construction. The rail damage emerged more gradually, but proved more economically devastating. Chief Track Engineer Raymond Haze documented gauge spreading that accelerated catastrophically under Big Boy operations. Standard 131-pound rail sections designed for maximum wheel loading of 65,000 pounds experienced plastic deformation when the locomotives applied full tractive effort during grade climbing. The 68-inch drivers concentrated forces that literally pushed rails outward, spreading gauge from the standard 56.5 inches to dangerous 57.2-inch measurements within 6 months of big boy service inauguration. The spreading created harmonic oscillations in freight car trucks that destroyed bearings and generated derailments at frequencies that made the territory nearly unoperational. Haze calculated that maintaining acceptable track geometry under big boy operations required complete rail replacement with 155-pound sections throughout the Wasatch Territory, 14,300 tons of steel that cost $8.2 million to fabricate and install. The expense exceeded the original locomotive purchase price by 340%. But the truly catastrophic infrastructure crisis emerged at terminal facilities designed around conventional locomotive dimensions. The 135-foot big boy length made existing turntables mechanically obsolete. Ogden's 120-foot turntable could not accommodate the locomotives, requiring complete replacement with 135-foot units that cost $480,000 each. Roundhouse modifications proved equally expensive. The big boy's width cleared existing stall doors by margins so narrow that thermal expansion during firing could cause the locomotive to bind against masonry walls. Rebuilding 12 roundhouse facilities to accommodate the behemoths consumed $6.8 million in construction costs. Shop Superintendent Thomas Crawford submitted reports documenting that routine big boy inspections required twice the time that conventional mallets demanded. The articulation joint needed complete disassembly every 90 days, consuming 480 man-hours per locomotive. The thermic siphon maintenance that Fetters had dismissed as manageable required firebox removal that tied up shop capacity for 3 weeks. Within 18 months of big boy introduction, Union Pacific's Civil Engineering Department calculated total infrastructure modification costs at $43.7 million. The 25 locomotives cost $16.5 million. They had purchased motive power that required spending $2.65 for every dollar of locomotive investment just to make the railroad capable of handling what they had ordered. Omaha's mechanical department discovered by late 1943 that the big boys represented maintenance complexity that exceeded anything steam locomotive servicing had previously encountered. The machines weren't just large, they were systemically incompatible with established shop protocols and tooling capabilities. The articulation joint failures began appearing at 45,000-mile intervals instead of the 180,000-mile service life that Alco's engineers had guaranteed. The massive hinge pin connecting front and rear engine groups experienced fretting corrosion that required complete replacement. Each pin weighed 890 pounds and cost $4,200 to fabricate with the chromium-nickel alloy specifications the design demanded. But replacement required specialized hydraulic presses that Omaha shops did not possess. Union Pacific had to contract with heavy industrial facilities in Cleveland, shipping failed components 200 miles for repairs that consumed 6 weeks per incident. The downtime transformed the locomotives from operational assets into shop liabilities that couldn't generate revenue while waiting for external repairs. Shop foreman Harold Mitchell documented that standard locomotive lifting equipment could not handle the big boys' weight distribution. The 548,000-pound locomotive exceeded the capacity of conventional wheel-drop tables, requiring construction of specialized lifting machinery that cost $185,000 per installation. 5 major shop facilities needed this equipment, consuming capital that could have purchased 3 additional diesel-electric locomotives. The driving wheel maintenance revealed another engineering miscalculation that specifications had not anticipated. The 68-inch drivers with their 5-inch diameter crank pins transmitted such enormous forces that the brass bearings failed at 22,000-mile average intervals. Standard locomotive practice expected 90,000 miles between bearing replacements. Each bearing replacement required removing the 8,400-pound side rod assembly, a procedure that demanded 4 machinists working 16-hour shifts. The brass-bearing material alone cost $340 per axle, and the precision machining to restore proper clearances added $890 in labor charges. With 16 driving axles per locomotive, bearing maintenance alone consumed $19,680 annually per unit. The firebox maintenance that Fetters had designed for maximum steam production created access nightmares that made routine inspections economically prohibitive. The Nicholson thermic siphons required inspection every 180 days to prevent catastrophic boiler failures. But accessing the siphons meant removing brick arch supports, dropping ash pans, and disassembling stay bolts, work that consumed 340 man-hours per inspection cycle. When siphon failures occurred, the repairs required complete firebox removal, a procedure that tied up shop capacity for 23 days. The replacement siphons cost $8,400 each, and the locomotive remained out of service for periods that exceeded the total annual downtime of 3 conventional mallets combined. Superintendent of Motive Power William Jeffers calculated in December 1944 that big boy maintenance consumed 47% more shop resources per ton-mile of freight moved compared to the 2880 mallets they were supposed to replace. The locomotives delivered the tractive effort that specifications promised, but the engineering optimization for raw power had created maintenance dependencies that made them economically inferior to the supposedly obsolete power they supplemented. The shop reports documented something that wartime emergency had obscured. Engineering excellence meant nothing when the machines you created couldn't be maintained with the infrastructure and expertise your organization actually possessed. By 1945, Union Pacific's operating department faced the sobering reality that the big boys had not solved the Wasatch grade problem. They had merely exchanged one set of operational constraints for different, more expensive limitations. The locomotives delivered their specified 135,375 pounds of tractive effort, exactly as Alco's engineers had promised. Single big boys could move 5,800 ton consists of grades that previously required double heading, but the infrastructure damage they inflicted made operating them at designed capacity economically suicidal. Dispatcher Harold Thompson's route bulletins documented the cascading restrictions that operational experience had forced upon big boy assignments. Maximum speed limited to 35 mph on tangent track due to frame oscillation that destroyed ballast. Bridge crossings were restricted to 15 mph to prevent dynamic loading that exceeded structural capacity. Curve speeds reduced to 12 mph because lateral forces at higher velocities spread gauge beyond safe tolerances. The restrictions meant that big boys moving 5,800 tons averaged 18.4 mph between Ogden and Green River, marginally faster than conventional mallets moving 3,200 tons at 16.2 mph. The tonnage advantage looked impressive until operations calculated actual economics. Each big boy trip consumed 47,000 pounds of coal compared to 26,000 pounds for the mallets. Maintenance cost per mile ran $4.85 for big boys versus $2.21 for conventional power. Track damage from big boy operations required maintenance expenditures of $1,240 per route mile annually, compared to $380 per mile under mallet operations. Transportation economist Robert Young analyzed the complete operational picture in his 1946 report to Union Pacific's Board of Directors. The big boys moved 81% more tonnage per trip, but cost 167% more to operate when infrastructure damage, fuel consumption, and maintenance were properly accounted for. The locomotives were technically superior and economically inferior simultaneously. The comparison with emerging diesel-electric technology became devastating by 1948. EMD's new F-Series covered wagons could pull 4,200-ton consists at sustained 40 mph speeds with fuel efficiency that made steam operations look wasteful. 4F units cost $600,000 to $80,000 combined, matching a single big boy's capabilities while consuming half the maintenance resources and inflicting minimal infrastructure damage. Young's analysis showed that diesel locomotive operations generated track maintenance costs of $190 per route mile compared to the big boys' $1,240. The difference alone justified complete fleet replacement within 3 years of diesel introduction. Union Pacific's board had resisted dieselization throughout the war years, believing their massive steam roster represented modern motive power. The big boys had proven exactly the opposite. The cruel irony became apparent in operating department meetings where superintendents discussed the locomotive's future. The machines worked perfectly according to their engineering specifications. They delivered the unstoppable tractive effort that wartime emergency had demanded. But peacetime economics required operational efficiency, not just raw pulling power. And efficiency meant accepting that over-engineering for maximum capability created locomotives that were simultaneously too powerful for existing infrastructure and too expensive to operate profitably. The big boys represented engineering triumph and operational failure embodied in 1.14 million pounds of perfectly functioning, economically disastrous machinery. July 21, 1959. Union Pacific Mechanical Superintendent Louis Burns watched Big Boy 4024 complete its final revenue run into Cheyenne, Wyoming. 25 massive articulated locomotives, each representing engineering capabilities that had exceeded every specification, were being systematically retired after just 18 years of service. The preservation of 8 big boys for museum display would ensure their legend endured, but the operational reality told a different story than the romanticized narrative of unstoppable steam power. The locomotives had worked exactly as designed while simultaneously proving that meeting engineering specifications wasn't the same as solving operational problems. The complete cost accounting revealed numbers that justified every regret the original design engineers had quietly harbored. The 25 big boys cost $16.5 million to purchase, but required $43.7 million in infrastructure modifications, $28.4 million in specialized maintenance equipment, and generated $67.2 million in accelerated track and bridge repairs over their service lives. Total investment per locomotive averaged $6.23 million when all costs were properly allocated. Contemporary diesel-electric locomotives delivered equivalent capabilities for $850,000 per 4-unit consist, including the infrastructure modifications they're lighter. Weight and lower tractive effort required. Union Pacific's financial analysts calculated that the Big Boy program had cost the railroad $127.5 million, more than achieving identical freight capacity through conventional articulated mallets supplemented with helper service. The wartime emergency that had justified the expenditure lasted 4 years. The financial consequences persisted for 2 decades. But the engineering lessons transcended railroad operations, offering insights that would influence American industrial design for generations. The big boys demonstrated that optimizing for single performance parameters, in this case, maximum tractive effort, without considering systemic integration, created solutions that technically succeeded while operationally failing. Modern heavy-haul railroads moving 15,000-ton coal trains use distributed power systems with multiple diesel-electric locomotives programmed to coordinate tractive effort while limiting infrastructure stress. The technology reflects lessons learned from big boy experience. Raw power means nothing without infrastructure capable of sustaining that power economically. The preserved Big Boy 4014, restored to operation by Union Pacific in 2019, demonstrates capabilities that still impress modern observers. The locomotive can deliver its designed 135,375 pounds of tractive effort exactly as it did in 1941. But Union Pacific operates it only on routes that have been specifically reinforced to handle the stress, at speeds that prevent the infrastructure damage that plagued original operations. The big boys provided permanent testimony to a principle that engineering education sometimes forgets. Excellence measured against specifications doesn't guarantee excellence measured against actual operational requirements. The locomotives worked perfectly. The system they operated within could not accommodate that perfection. Otto Jabelmann, who designed the specifications that created these machines, wrote privately in 1952 that he would have recommended rejection if he had understood the total cost implications. "We built exactly what we asked for," he noted in correspondence with Alco's engineering department. "Our mistake was asking for something the railroad could not actually use." The lesson remains relevant. Engineering triumph requires wisdom to know when maximum capability creates minimum value.